Oh, you're probably just wrapping things up. When you get done, feel free. Oh, some of you have. Put your little papers over towards the middle here. You're happy with this? Close enough, good enough. So we've approximated our approximations. Nice. Oh, yeah, I've got yours. Oh, thank you. Excellent. Very nice. Wow. 10 digits. I have not. Matthew here wanted to know as well. So I'll get it figured out tomorrow. Tomorrow's my thinking day. So probably I'll have somewhere online. The stuff for Friday though will be a piece of paper because it's Taylor series. So. Take a peek. Coming down the home stretch. Very nice. Got the last couple digits there. All right. Let me hover over you. There we go. Good job. Very nice. All right, what do you think? Got that last piece down. Let's see what we're doing. Good enough? Good enough. Excellent. Okay, so I noticed that there's a minor discrepancy on that last one with the sign, and that's because some of you are in radians and some of you are in degrees. So I didn't specify, so I guess I should take both versions, but mine is in radians, just so you know. Oh, do I have all the quizzes? All right, I just want to make sure before I staple. Okay, so let me show you what I have when we get to the last one. Remember, if you're in degrees, you'll have a different answer than me. I guess I just assume that all calculus is done in radians, and this is kind of a subset of calculus here. Okay, the first one, absolute error. By the way, each one of these things is an approximation that some people use in real life. So for example, when I'm doing calculations, trying to figure out something to do with powers of 2, I just know that 2 to the 10th is approximately the same as 10 to the 3rd. So if I want to approximate 2 to the 20th, 10 to the 6th. So anyway, how far am I off when I do this? Well, 24 is the absolute amount that I'm off. By the way, this also helps you figure out logarithms base 2, compare them. But anyway, so how far am I off is a relative error. So here's the one thing to make sure that you note, and that is that the relative error is computed when you compare how far you are, the absolute error, divided by the actual number, the actual. So if you put 1,000 down here and 10 to the 3rd is 1,000 instead of 1024, then you're wrong. So it's actually about 2.3% is the relative error. So there's that. That's one place that you might have made a mistake. Okay, the next one, you might wonder, what are those? Well, what's the acceleration due to gravity? 32 feet per second squared, right? Wrong. 32.174 feet per second squared. So this is what all high school physicists or physics kids learn about the acceleration due to gravity. So how far off are we when we use 32 instead of 32.174? Oh, by the way, it's not even that. There's a range depending on where you are on the world in the Earth. It varies between 32.05 or so and 32.3, I think is the, so depending on how much stuff there is below you, like if you're on top of a mountain or over the ocean. But anyway, so this is an average for the whole world. So that's how far are we off absolute error. And then this is the relative error. So only about a half of a percentage. So I think we're doing pretty good for our high school physics people. The next one, ooh, do you have any people want to guess what 3.107 is? It's the number of miles in 5K. So pi day 5K, we run pi miles, 3.14 miles. So that's like an approximation. Anyway, so I was just curious, like how far off are we when we do pi miles instead of 5K miles, or 5K instead of 5 whatever. And so this is the absolute difference, and then we're about a 1%. So that's not too bad at all. So 1.1%. Okay, now the one that a lot of people, well, not a lot, some of you, I noticed, had different answers than me, and it's because of this. But you might wonder, what is this all about? Well, for small values of theta, sine of theta equals theta, approximately. So the smaller the number, the closer you are if you're in radians. So in radians, this is true, not true in degrees. So when you're in radians, sine of theta is approximately theta for small values. And so here's how far off you are in absolute terms in radians. In degrees, of course, it's going to be way off. It's like 0.49 or something. And then this is a 4%, 4.2% error. So that's a little bit large. But if you did this again for 0.1, you'd find that sine of 0.1 is very close to 0.1. So just an interesting little fact there. So hopefully you have something similar and you get 100% on this, because it is our first quiz. Even if you don't have 100%, that's okay. You probably got close to 100%. Yeah? Well, we're doing absolute value, so it doesn't matter. Yeah. Yeah, it's irrelevant, because you do the absolute value and it gets rid of any plus or minus. Yeah, so one of the things, if you haven't had me before, is, or for Matthew or anyone else that can't remember, when I do my test is sort of like I take all the quizzes, put them all together, and then I get rid of some stuff, and that's the exam. So that's one of the benefits of taking the quizzes, is it gets me to see how things are going. It gets you to see how things are going, and we can go from there. Okay, today we need to switch gears to talk about not this, Taylor series. So let me find my Taylor series. Hold on a sec. Where did I put this? It was on wherever my stuff was for Monday. Oh, here it is. I think it's here, I hope. Let's see. Yes, it is. Yay. Okay, calculus review. So calculus review. So what we're going to be doing is, so Taylor polynomials. Oof, let me get rid of this outline. That's better. Okay. We started this last time, but I just want to remind you a couple of things about Taylor polynomials. And the reason for this is that by far the strategy that we're going to be using to solve things on the computer, to teach the computer how to solve things, is we're going to first of all think about what a Taylor polynomial looks like and how whatever it is that we want to do works with Taylor polynomials, and then we will do it, for whatever function we have. And the Taylor polynomial, the beauty of using the Taylor polynomial as the starting point, the stepping stone, is that the Taylor polynomial gives us estimate for the error. And so that's the main thing. So today we're going to just review Taylor polynomials and then practice a few times. So what is a Taylor polynomial? Well, let's see. I've got the actual definition here. And that looks really scary. So I know we kind of hinted at this last time, but here's the actual definition. And in fact, what we'll do is maybe I'll just take that formula and move it over where I can actually do some work with it. So give me a sec here. And yeah, I guess I have some examples that we can do, But let's just go over here. I can copy the examples. So I'll go over here, paste this back in. There it is. Okay, so there is the Taylor polynomial. Now there's also what we need to do is we need to deal with the error, but we'll do that next. So we'll do the Taylor polynomial first, just to remind you how this works. So let's do something pretty simple for this thing. So so let's do the Taylor polynomial for just a minute. Let me go back and see what I had on my next slide. Sine of x, 1 over 1 minus x, square root of x squared plus 1. E to the x is too easy. Let's do sine of x. Sine of x. All of these are pretty simple. Yeah, we'll do sine of x. It's not the most fun, but we can do it. Okay, so we'll do sine of x. So we're going to do the Taylor polynomial for y equals, or no, not y, f of x. F of x is equal to sine of x centered at x equals 0. I'll explain what all this is. And I guess I need to specify what degree. Let's do p sub 3. So the third. So that means p sub 3. So third Taylor polynomial for sine of x centered at x equals 0. Yeah, that'll work. It's not going to be very exciting, which I know is disappointing for you, but it'll work. By the way, this Taylor polynomial, you'll notice, ends at whatever number you're choosing. So I'm choosing n, or 3 here, and that's where I stop the Taylor polynomial. Taylor's theorem says that if you do the limit as n approaches infinity, the series, the Taylor series, is identical to the function f of x on some interval, I should say. There's a convergence. You probably remember this from calculus 2. It may be that it was so painful that you've tried to block it out of your mind. It's okay. All we really need to know are 2 things about Taylor polynomials. First thing is, how do you construct them, which we're going to review right now. The second thing is, how far off, what kind of error can we expect if we use a Taylor polynomial? So let's go ahead and do this for this particular function. So the Taylor polynomial for sine of x centered at x equals 0. So the first thing I want to do is I'm going to have to compute the derivatives. So notice that up here, we're going to have to compute the first derivative, the second derivative, and the third derivative. If this was the fourth Taylor polynomial, I would compute the fourth derivative. The fifth Taylor polynomial, I would keep going, fifth derivative. But here, just the third derivative is as far as I need to go. So you guys can help me with this because you know your basic calculus. And if you don't, then we need to shame you. No, I'm just kidding. If you don't, you can just take a guess and it'll be okay. So let's see, we have, usually when I do this, here, I'll show you. I'm going to go way over to the right onto a piece of scrap paper. And I usually do something, make a little table. So I've got f of x is sine of x, and then I have f prime of x, f double prime of x. Now, I know some of you are sloppy. And the only reason I mention this is because I was sloppy. I was terrible when I was learning calculus. And I'm sure, I am confident that I got some things wrong because of my sloppiness. You know, and I see this, like in the morning, I have Calc 2. Some students are getting problems wrong, not because they don't know the calculus, but just because they're sloppy and not being careful with their notation. So try your best. Take it from me. I know it's hard, it's a pain, but you can do this. Okay, so Eli, do you know the derivative of sine of x? It is, very good. Derivative of sine is cosine. Cosine of x. Julia, what about the derivative of cosine? Negative sine. So that means that the second derivative of sine is negative sine. Okay, now we can keep going because we only need the third derivative. So let's just get one more. Breyer, what's the third derivative of sine? Yeah, so you do another derivative, you do negative cosine. Good job. Okay, so that's as far as I need to go. And the reason that I'm going to stop there is because I'm going to get my third Taylor polynomial. So stop after 3. I'm going to leave a little blank here, though, because, so let's just make sure that you leave some room down here because, okay, let me just point out that eventually I'm going to care about the fourth derivative, but not yet. So for now, I'm going to draw a line here. Eventually I will care, but not yet. Okay, so there's that. And then over here, c is equal to 0. So on my Taylor polynomial formula, you'll notice that there's this c. The c represents the center of the polynomial where it converges. And so that center is written there. I wrote it as centered at x equals 0, but I don't know how this, I guess I could switch to the book. We'll see what it is. They might have a c there instead of an x. Well, whatever it is, the center is that c. So up here, I'm going to plug in c equals 0. And the reason for that is that the Taylor polynomial coefficients rely on the values of these things evaluated at c equals 0. So let's go ahead and do that. When you plug c equals 0 into the sign, I get sine of 0. And don't forget to put your calculator in radians, because even though this isn't calculus, it is relying on calculus. So from now on, this class, radians are the way to go. Sine of 0 is 0. Then we have cosine of 0, which is 1. And then the negative sine of 0, which is 0. And the negative cosine of 0, which is negative 1. So far, so good. Next, we've got to plug those in. So I'm going to, I've got it all zoomed out here, but I'm going to zoom in because I have this stuff memorized. You can refer back and forth if you want to, but I'm going to plug these into this Taylor polynomial formula. And then hopefully we'll have our nice third degree Taylor polynomial for sine. Okay, so I'll just refer up there. So f of c, that's f of 0, that's 0. F prime of c, that would be f prime of 0, was 1 times x minus 0. And then the second derivative was 0. I know this is kind of unnecessary, but I'm going to write it anyway. And then the third derivative was negative 1, if my memory serves me correct. X minus 0 cubed. I'm going to clean this up because there's no reason for me to have all these zeros lying around. I've got x minus 1 over 6 times x cubed. So it turns out that this is actually close to sine of x. Well, when you're close to 0, that is. So when you're close to the center of whatever it is, wherever your Taylor polynomial is defined, then you're going to be close to sine of x. Let me just see if I can find, just a sec. Just realized that I should, well, maybe it's going to be too hard to find, I think. Maybe not. Hold on a sec. Taylor polynomials. Let me see if this works. I'll show you what I'm showing, what I'm doing in just a sec. Okay, I got to just start from the start. Should have had this set up before. Okay, yeah, this is good. This is fun. Okay, so this is not Python, sadly, because when I wrote this, I didn't know Python. But someday, maybe I will be cool and change this to Python, but this is a cool demonstration of Taylor polynomials. So here's the sine curve. So, and this sine curve, if you superimpose the first Taylor polynomial, or the zero Taylor polynomial, you get just a constant, x equals, or y equals 0. That's boring. So then the first Taylor polynomial, wait, where is it? Sorry, I'm not pressing the right button up here. There we go. There it is. So this line, that represents y equals x. So here's sine. This is y equals x. So that's the first Taylor polynomial. Let me go back to this here. That first Taylor polynomial is this right here. So if we stop there, you get y equals x. Now let's say that we stopped with the second Taylor polynomial. You would have y equals x plus 0. So it's still just y equals x, boring. But I have that here anyway. Well, maybe. There it is. Okay, there it is. So let's do this. So there, I've advanced. Believe it or not, that's a different Taylor polynomial. Looks the same. It's still y equals x. Now let's go to that third Taylor polynomial. This is where things get really interesting. So yeah, eventually I'll do this on Python. Where is it? There we go. Look at this. Look how close this is to the sine curve between like here and here. It's pretty darn close. How close is it? Well, that's where the remainder theorem comes from. But how close it is going to depend on how far you are away from the center. The center is right there at 0. We'll come back to this because there's an interesting thing we can do. But for now, let's just actually ask the question, how close are we? So how close will this be? Now, in order to ask the question, how close, whoops, I need to specify how close will P3 of pi over 2 be to sine of pi over 2. So essentially, when I ask about how close, I need to know what am I approximating. So how close will that be to this? Now, certainly, we could actually compute sine of pi over 2. We know what sine of pi over 2 is. Sine of pi over 2 is 1. You could compute this by using this polynomial, easy. But Taylor has a remainder theorem that says that if you stop after the nth, so here, after n, the remainder, that is how far you are away from the truth, is something very predictable. Using the mean value theorem, in fact, it's going to look very similar to the mean value theorem. The remainder is going to be based on that. Now, where is my remainder? Oh, wait, it's not printed here. Guess I just have to do it from memory. Okay, so the remainder, how close will it be? Question mark. What we're going to do is we're going to compute what's called the remainder. The remainder, R3 of x, is equal to the next term. With a little asterisk. I'll explain why. So what do I mean by the next term? Well, if you were to continue, notice here, see this, if you stop at f sub n, then the next term, f n plus 1, n plus 1 factorial times x minus c to the n plus 1. That's the next term. That's what I mean by the next term. Now I've left the parentheses empty, and the reason is that when I say the next term with a little asterisk, I mean it's the worst case scenario for the next term. Now here's what I mean by that, is if I'm going to approximate, if I'm going to use P sub 3 to approximate sine at pi over 2, then what's the worst that could happen? Well, the worst that could happen is that this, whatever goes in here, makes this really big. So essentially what you have to do is you have to do a little bit of I guess, analysis of the function that you're dealing with. So here's the way that I would write this. Just a minute. I'll just copy this. This is almost correct. Here, copy. So here I'll paste down here. Let me just get rid of that arrow and I'll put something else in there. So I'll put, I think the book has Xi. I know, it's like a weird Greek letter. So that Greek letter just represents, this is the let's see, it's not really the worst case scenario. Okay, so the deal is that the remainder, how far off you are, you're guaranteed, just like the mean value theorem. Mean value theorem says you're guaranteed to find a point somewhere between A and B where the slope is equal to the average slope. This is very similar. You're guaranteed to find some point between the center and whatever point you're estimating where the remainder is equal to this exactly. And so because that's the case, to compute the error or to estimate the error, what we do is we do a sort of analysis of what's the worst that could happen. So that's what we're going to do here. What's the worst that could happen between 0 and pi over 2 for this expression? So let's actually do that. R sub 3, I'll show you exactly how this works. I get the fourth derivative. So the next term is the fourth derivative. I'll just put C there. And then this is going to be 4 factorial. X minus c to the fourth power. Now let's deal with this, first of all, the fourth derivative. So we know that the fourth derivative of sine of x is actually sine of x, right? Because the third derivative was negative cosine. So that's why I said we're going to have to deal with this eventually, so I left it there. Okay, so third, the remainder third is we're going to use the fourth derivative. So now the question becomes this. First of all, c is equal to 0, x is equal to pi over 2. So r sub 3 of pi over 2, we'll get to c in a minute. Pi over 2 to the fourth. Okay, so this thing is centered at 0. The x, this is the thing that I'm trying to approximate, is sine of pi over 2. Now, here's the deal with this term up here. What you're going to do is you're going to take that and write it over here. Let's see. Yes? Oh, no, it's r sub 3. Sorry. Yeah, so yeah, the deal is, sorry. We're going to approximate our function with a polynomial, and the remainder for that polynomial, it always matches the number. And I realized that that number, whatever's down here, you have the next number. Yeah, so it's always the next term. So even though it's r sub 3, you use the fourth derivative. So it does feel like everything's 4s, but it's the remainder term for the third degree polynomial. Yeah, so we'll practice this in a minute with a couple other functions, but let's just see if we can pound through this. So write down the fourth derivative. So the fourth derivative is the sine of x. So that's up here. Where is it? There it is. Fourth derivative is sine of x. So how big can sine of x be between, oh, maybe I should put a c there. No, I'll leave it as sine of x. I'm just trying to think of the way to make it as easy as possible for you. So you're doing sine of x where x is between 0 and pi over 2. So 0 is the center. Pi over 2 is the number I'm trying to approximate. And so I want to know, what's the worst case scenario? How big? What's the biggest that sine of x can be when you're between 0 and pi over 2? Now, fortunately for us, we're all familiar with sine of x, so that shouldn't be too difficult. Do you know what the biggest that sine of x can be between 0 and pi over 2? Or better yet, the biggest it can be ever for any number. So what is it? What do you got, Eli? Yeah, it's 1. Yeah, the sine of x is just as big. The biggest it can ever be is 1. The smallest is -1. But in absolute value, the biggest it can ever be is 1. So the worst case scenario is that this is 1. So what that means is that my remainder is going to equal some number between 0 and pi over 2. Well, you're going to plug some number in here, but the worst it could be, it's always going to be less than or equal to 1. So that's the idea there, and then this is going to be pi over 2 to the 4th. So let me just see what this is on my calculator to see how far off I'm predicting I could be. So let's see, 1 over 24 times pi over 2 to the 4th power. So I'm getting 0.254, which is pretty big. I mean, it's a pretty big difference there. But what this tells me is that if I use this polynomial to predict or to estimate or approximate the sign of pi over 2, then this is as bad as it can get. So going back to my little picture, you'll see that, in fact, it's not even that bad. See, this is the polynomial, and this up here, the red one, is the sign. And you can see it's clearly less than 0.25. 0.25 is the maximum possible error. But you can also see that the closer you get to here, the less the error. And the reason for that, of course, is because if you were trying to approximate the error for doing, let's say we did pi over 4, then you would put pi over 4 in here instead of pi over 2, and this c would be something between 0 and pi over 4. And pi over 4, the sign of pi over 4 is 0.707. So the most that this could be would be 0.707, and that would reduce the overall error estimate. Well, let's see if we can do one of these so that you see how this goes. Let's see, I have my book here. That might be better. Yes? The highest possible error when you are approximating the sign of x using this polynomial. When this is only for pi over 2 though. If you use this polynomial like over here somewhere, then it's definitely way further away. So that's only like from here to here or something. That's where that's valid. Yeah. Okay, so let's see if let's take a look at one of the book problems just so that we can get a feel for how these work. Let's see, go to the end of this section. Here we go. Okay, just so you get used to the language. So notice that this is saying find t of 3, t sub 3 of x, and r sub 3 of x for each of these functions. So let's skip down to letter F, or better yet, letter G. Yeah, G looks more interesting. So actually, those are all boring. Now let's skip down to this. So let's do number 2, just to get started on this. So that's boring as well. Sorry, these are all so boring. I mean, well, okay, it's not boring. It is what it is here. Man, yeah, I mean, I've assigned the boring ones. You want the boring ones for your homework, so that's good. Okay, I don't like any of these. You see the language though. So this is the sort of thing you're going to have to do. Let me pick something that's less boring. So give me a sec here. Switch over to here. What I'd like to do is I would like to compute t sub 3 and r sub 3 for f of x is equal to arctan, of course arctan, centered at x equals 1. Yeah, just to make it a little bit different than, so this is way harder than your homework. So this will be, if we can do this, we're going to be good with the homework. I guess there are some questions, some nuances on the homework that might cause difficulty if we don't get to them, but yeah, we got 13 minutes. We'll do this one for sure. Okay, so let's do this. So you know the drill now. your first step when you're approaching this, I want a third degree polynomial and I want a remainder term. So the first thing is to start with the function and compute the derivatives. Arctan. So let's get the, oh, I guess, there we go. This is f. I need f prime, f double prime. There we go. So we're going to need those 4 derivatives. The fourth one is only for the remainder term, though. Now I'm already starting to dread the derivatives, but we're going to do this. It's going to be okay. So let's see who's going to do the first derivative. I know you know it. Well, most of you do. Alyssa, do you know what the derivative of arctan is? You don't? Oh, you didn't have me for calculus. That's why. Let's see. Let me find someone. Grayson knows. Wait, you didn't have me for calculus either. But do you know it? Okay, wait. Let's see. Let's see. Who's got? Wait, who wants to tell me? You know it. Yeah, Rachel knows it. Yeah, 1/1 plus x squared. Yeah, yeah. It's okay. It's one of these transcendental functions that some people don't care about, but I love. So, okay, so there it is, 1/1 plus x squared. Now we'll do the. Now that we have that, it's a nice rational function. We can do the derivative of that. That's not too bad. It's the third derivative that I'm not looking forward to. So go ahead and take that first derivative, do the second derivative. By the way, let's here, I'll make things easier on you. That's the same as 1 plus x squared to the negative first power. That might be a little easier, I don't know. Well, Zane, do you have the second derivative? Use the chain rule? You can do it, come on. With this thing? Ooh, nice, he's got it. But, yeah, so we got, let me do it. Let me do the chain rule. That way we'll get it all clear because there is a 2x and there is a fraction, but let's actually do it carefully. So this thing ends up being -1 times 1 plus x squared to the -2. You remember doing this chain rule? It's feeling good, doesn't it? And then times 2x. So one way to write this, now I keep moving my line, is to write it like this, -2x over 1 plus x squared squared. I've been avoiding it, but I don't think I can anymore. We're going to have to use the quotient rule, aren't we? Okay, I know. Well, it's okay. We got the time. We can do it. So let's do this quotient rule. I'll go ahead. Low d high minus high d low over low low. You remember this? Okay, so low d high. So this is going to be 1 plus x squared squared times -2.